Right. Yeah, welcome everyone to the new season of Reset, and we're really happy to have Alex Wolitzky here to start the new season, who's going to present Marginal Reputation, which is joined with Daniel Lowe, who's also here. So if you have any questions, you can also post them in the chat, and Daniel will uh, uh, look at those questions and try to answer. And then we're also very happy to have Elliot Liplowski and Jeff Ely here, who are going to be panelists and asking questions to Alex during the talk. The talk is 1 hour, and then we have some time for discussion at the end. We are recording the talk, so be aware of that if you have your video on. And yeah, that's it. Alex, the screen is yours.
Okay, thanks very much. Thanks for inviting me to give this talk. Thanks for coming, and yeah, thank you to Elliot and Jeff for serving as panelists. Let me start with a quote from Tom Schelling. So this is Schelling writing, I think this one's from Arms and Influence. And so he writes, any coercive threat requires corresponding assurances. The object of a threat is to give somebody a choice. To say one more step and I shoot can be a deterrent only if accompanied by the implicit assurance, and if you stop, I won't. Giving notice of unconditional intent to shoot gives him no choice. So the point that Schelling is making here is that deterrence is a setting where a player wants a reputation for conditional action. So in this case, shoot if you take another step, don't shoot otherwise. And there are a number of settings in economics and game theory where players want a reputation for conditional action. So deterrence is one. Another that I'll talk about today is communication, where a sender wants a reputation for sending a certain message, say a suggestion that a receiver should take a particular action in some states of the world, but not others. So what we study in this paper is reputation formation in repeated games where a long-run player wants a reputation for conditional action, for taking certain actions after some signals they might observe, but not after others. Okay, so is this a new problem? Well, if we think about games where the long-run player's strategy, so the map from the signal she observes, say a signal of the opponent's action in a deterrence setting, or her observation of the state in a communication game, the mapping from that signal to her action is observed, then this would not be a new problem. This would be we would be studying reputation formation in a repeated game where the long-run player's strategy is perfectly observed. This is a well-studied problem going back, for example, to the seminal work of Feuderberg-Levine in the 80s. However, we think it's often more realistic to think that only the long-run player's realized action is observed. So, for instance, in a setting of deterrence, potential attackers may observe when the long-run player fought or retaliated in the past, but not what signals the long-run player observed that may have led her to behave in that way. Or in a communication game, receivers may see the history of the signal sent by a sender or the history of messages the sender sent in the past, but may not observe the corresponding states of the world. So receivers may see, well, exactly the history of messages, the long-run player's actions in that setting, but not the history of states. So these settings that we're studying then are ones where we're considering reputation formation with a particular form of imperfect monitoring of the long-run player's strategy. So we're focusing on settings where the long-run player's strategy is a mapping from some private signal to an action, and the marginal distribution over the long-run player's action is observed, but the joint distribution between the signals observed by the long-run player and her actions are not observed. And we're asking, how does reputation formation work in these settings when the long-run player is going to get some kind of private signal and then take an action, and the action is observed by short-run players, but the signal and hence long-run player strategy is not observed. Okay, so as we'll see, this is again a kind of setting of reputation information with imperfect monitoring. Standard results in reputation with imperfect monitoring are going to be vacuous in this setting. And the reason is that the long-run player strategy is just very much not identified in these games. And that's going to, as we'll see, imply that known bounds long-run players' payoff in these settings are going to be essentially vacuous. So our question is going to be, when can long-run player nonetheless successfully build a reputation in these settings? So, when can our deterring guy successfully establish reputation for deterrence? When can a sender establish reputation for playing a particular signaling or communication strategy? Again, when only their actions and not their strategy is observed. And we'll show that that's the case if, and in some settings only if, the Stackleberg strategy, the strategy to which the long-run player would most like to publicly commit herself, satisfies a condition that we call confound defeatingness. And what confound defeating means is that, well, from the long-run player's perspective, this strategy is better than or defeats any possibly confounding strategy, any strategy that could generate the same marginal over actions and could thus be confused by the short-run player with the strategy to which the long-run player actually wants to commit. So a bit more precisely, this confound defeating property says that the Stackleberg strategy is uniquely optimal for the long-run player among those strategies that generate the same marginal over actions against any sort of best response to the short-run players in a way that we'll make precise. In particular, this property corresponds to this Stackleberg strategy, meaning the unique solution to a particular optimal transport problem. We'll of course see how this works more precisely. An implication is going to be that in a leading class of games, supermodular games with one-dimensional signals and one-dimensional actions, the long-run players can be able to secure her Stackleberg payoff if and only if her Stackleberg strategy is a monotone function for her signal to her action. We'll then talk about applications to communication games. And in particular, we're going to provide a foundation for the commitment solution in repeated signaling games or in repeated cheap talk or persuasion games in which the sender's preferences over the receiver's actions are state independent. And in the case of cheap talk games, this result's not going to apply literally the cheap talk game per se. It's going to apply to the cheap talk game augmented with some small lying or deception costs. So turning this cheap talk game into a signaling game with small signaling costs. I should say, please feel free to jump in with questions at any point. I feel like I'm just talking to a screen for an hour. It's taking a little bit dry. Okay. All right. So what do we relate to? Several strands of literature. So most directly, this is a paper on reputation in repeated games, going back to Feudor McLevine and others. Jeff's great paper with Yusuf Alamaki, which our title is a bit of a tip of the hat. Key observation is that, as we'll see, the predictions of existing models' reputation with imperfect monitoring are going to be vacuous in our setting because those payoff bounds are sharp and the long-run player strategy is better identified in our setting where actions are observed but signals aren't. The mapping from signals to actions, which is what the long-run player wants to build a reputation for, is just very much not identified, and existing results are not going to say much about what happens in these games. We'll see this very concretely in an example in a moment. Our paper is kind of all about what deviations by the long-run player are going to be undetectable by the short-run player who only sees the marginal over action and not the strategy. And so we connect this literature in diverse places in mechanism design and game theory about, what can we say about games where some deviations are unobserved, and often this connects to some matching or optimal transport arguments. So we're related to that literature. I think we're kind of bringing those kind of ideas to study reputation formation. And then we also relate to literature on trying to provide a reputation foundation for commitment solutions in signaling or persuasion games. An observation first made by Ryo and Segal in their seminal paper on persuasion is that if the long-run player strategy is observed, so the map is so if short-run players observe the state in each period and also the long-run player's message, then Friedenberg-Levine's results are going to imply the long-run player, when patient, can secure her commitment payoff. So we're instead going to be able to extend that and give a foundation for these commitment solutions, even when short-run players don't observe the past states. They only see the long-run players' past messages, but not, the states behind them. Okay, so here's an ambitious outline. We'll start with showing the main ideas in the context of a simple deterrence game. Then we'll see our general model, our commitment or stackable payoff theorem. That's our main result. We'll talk about implications of this result in the context of one-dimensional supermodular games, and finally applications to communication games. Any questions at this point?
I have a question.
Please.
It's not a question that I'm super happy to ask, but I think it'll be informative. So I'm guessing that when you say that the marginal on actions is observed but not the joint, I think I'm guessing you mean the very strong assumption that the marginal on actions is observed and nothing at all about the realized signals has in the past have been observed.
Right. So it's going to be important that the publicly observed signals are identifying the long-run player's action, but not the joint distribution over states in action.
And so the question that I don't get a lot of pleasure in asking, but I think it's informative, is what if there was just a tiny bit of information that was informative about the correlation between the action and the signal, just a tiny, tiny bit?
Yeah. So, I mean, we haven't studied that, but my conjecture would be that then there'd be some order of limits business to worry about. You would need to ask, how much information you're getting about the strategy relative to how patient the long-run player is.
So fixing the information, no matter how bad it is, take the discount factor to 1, you probably get a positive reputation result.
I mean, not just probably. I mean, in that case, the long-run player's strategy is identified. So I think off the shelf, Friedenberg-Levine 92 would say that if you're really patient enough, you can establish reputation for your desired strategy. Yeah. But we don't think that's necessarily the realistic case.
And I mean, so if there's more information, but maybe it identifies or rules out some strategies, but not all of them, our results will still apply, because the more information I get about the signal, the kind of less unobservable deviations there will be. So you might get a little bit of information, it might not identify everything, but you can still apply our results to get a high payoff theorem.
And you stated the results at the beginning specifically about the Stackelberg strategy, but probably you have just some bound that depends on like what's identified and what isn't. And
exactly, we're stating our results in this that we state in the paper also as saying when you can secure your Stackelberg payoff. But again, just as in Friedenberg-Levine or most of the literature, the same arguments say when can you secure the payoff that you could get by publicly committing to any strategy. Thanks for the question. Okay, so let me spend some time on a simple example that's going to illustrate some of our main ideas. And this is going to be a deterrence game. So we have a single long-run player who faces a sequence of short-run opponents. The long-run player is patient with some discount factor delta less than 1. Each period, the short-run player is going to move first and can either be nice or nasty. She can either cooperate or defect. And the long-run player is then going to observe a signal of the short-run player's action, which we'll assume, for simplicity in our example, is a symmetric binary signal that matches the short-run player's action with some probability p greater than 1/2. And the long-run player is then going to either fight F or accommodate A. So the player's payoffs are given by the following matrices. Here we've expressed the short-run player's payoff as a function of the actions taken, and the long-run player's payoff as a function of her action and her signal. So the long-run player's payoff here is measured with respect to her own information. And these payoffs take the standard form of a deterrence game. So for the short-run player, defecting is dominant for any fixed action of the long-run player. But if the long-run player is playing her deterring or pure stackable strategy of accommodating when she sees the nice signal and fighting when she sees the nasty signal, that's going to deter the short-run player, and the short-run player is then going to cooperate rather than defect. Now, for the long-run player, she would like the short-run player to be nice and cooperate, but in the stage game, accommodating is dominant for the long-run player. The long-run player doesn't take any pleasure in fighting. And so that implies that if this game was played once, the unique equilibrium would have the long-run player always accommodating, and anticipating this, the short-run player would defect. However, if the long-run player could publicly commit herself to any pure strategy, she would commit herself to the Stackelberg deterring strategy of accommodating after signal C, fighting after signal D, and then the short-run player would be deterred, would cooperate, and the long-run player would get her Stackelberg payoff, which here is just P, right? Because if the short-run player cooperates and the long-run player plays accommodate after signal C, fight after signal D, the long-run player's payoff is going to be P. The probability the short-run player cooperates and then she accommodates. And we're going to consider the case where the long-run player is either rational with the payoffs given on this slide, or is committed to her Stackelberg strategy of accommodating after signal C, fighting after signal D. And we'll let mu naught be the prior probability that the long-run player is committed. And our key assumption is that we have this sequence of short-run players, and each short-run player sees the whole history of the long-run player's past actions, fight or accommodate, but not the underlying signals. Maybe I'll mention, I could have said this earlier, but maybe I'll mention now, one of the motivations for this paper was thinking about international relations, and in particular, the conflicts between Israel and various actors with Israel, with which Israel finds itself in conflict, and thinking about how could what kind of strategy might lead to peace in this situation. We're thinking about this kind of setting. These various hostile groups, they see perhaps how often or when Israel bombs a town or goes to war or whatever, but doesn't necessarily know kind of what signals or what reasoning the leadership had that led to these actions. So this is just one example, but this is the kind of situation we have in mind. We see these possible aggressors see when the long-run players fought in the past, but not necessarily why, not what signal led to that action.
Sorry, I'm guessing it's also important that the short-run players' past actions were not observed.
No, that's not important. That's not important. The short-run players' actions could be observed here, because everyone's using public strategies here. So there's not going to be any, at least in a pure strategy equilibrium, people could infer what the short-run player did. Right. What's going to be important, right, is that the long-run player's signal is not up here. Oh, yeah.
Sure. Actually, sorry, never mind. Sure. Yeah, I was going to ask a stupid question. I'll wait and ask stupid question later.
All right. Okay. So what is the what is the challenge of the long-run player? The long-run player, let's say, would like to establish a reputation for playing the Stackelberg strategy. She's possibly committed to it. So we might think that what the long-run player should do is just always play the Stackelberg strategy, accommodate after the nice signal, fight after the nasty signal, and hope the short-run player gets the idea and starts cooperating. So the question is that going to work? Well, if the long-run player plays her Stackelberg strategy and the short-run player cooperates, that is going to lead to the long-run player getting the nice signal with this high probability P and accommodating, and getting the bad signal and fighting with probability 1 minus P. So what the short-run players are going to see is that in the past, the long-run player fights 1 minus P of the time and accommodates P of the time. The problem, though, is that the short run players are going to see that same distribution of the long run player's action if rather than playing this Stackelberg strategy of fighting only after the bad signal, the long run player is playing some other strategies, such as, for example, just randomly fighting with probably 1 minus p in each period, independent of the signal they see. And so this is kind of the key problem. The short run players see how often the long run player fights, and actually they see when the long run player fights, but not why she fights, not what signal the long run player observed before taking her action. And this is a problem for the long run player, because if for some reason the short run players think that the long run player is, say, fighting uniformly at random rather than fighting when she sees the bad signal, the short run player is not going to be deterred. If the short run player thinks the long run player is fighting at random, the short run player thinks that his action has no bearing on the long run player's action, and so he'll take his myopic best response of defecting. So far, there's not much new here. In the language of Friedenberg-Levine, what this is saying is that defect, while it's not a best response to the Stackelberg strategy, the only best response to the Stackelberg strategy is to cooperate. It's what Friedenberg-Levine calls a zero confirmed best response to the Stackelberg strategy. And what that means is that it's a best response to a strategy that looks the same as the Stackelberg strategy. Right, so as far as the short run player is concerned, she's going to see the same distribution of signals if the long run player is actually fighting only when she gets the bad signal or when the long run player is fighting at random. So therefore, defect is a best response to fighting at random, and so it's a zero confirmed best response to the Stackelberg strategy.
Sorry, I hate to interrupt, but I just want to follow up with a question here. So this is mostly just for me to understand a little better. So the long run player sees this signal of the short run player's action, but the long run player doesn't see the short run player's actual action.
Correct.
Now, if the future players saw the short run player's action, and let's say the short run players were mixing, then wouldn't these two strategies look different to the future short run players? They'd see the realization of the short run player's random action, and they would predict a different conditional distribution of the long run player's action from these two strategies.
Yeah, that's true. Let me think about this. So maybe we can come back to this later. Yeah, so we're always looking at public strategies.
And probably you can't construct an equilibrium where the short run players are mixing. I mean, I don't know. So maybe it's not relevant, but I asked the question just because I wanted to make sure I understood how it matters about what the short run player's past actions observability is.
I think what matters. You're right. I think we are going to want that the long run player and the short run players have symmetric information about short run players' past strategies. That's probably something.
Yeah, that seems like guarantees that there's no.
Yeah. Actually, we'll see when we get to the model exactly what formalism we have. But yeah, I feel that that's what we need. Okay, so what the literature says is that the patient long runs player in any repeated game equilibrium is bounded below by her best commitment payoff when the short run player takes his least favorable zero confirmed best response. And the logic is simply that by playing say her Stackelberg strategy, the long run player can teach the short run player the corresponding marginal distribution over signals, the corresponding distribution over signals, but nothing more about the long run player strategy, at least according to arguments in the literature. And in this example, this says the long run player is not going to necessarily do very well because you know, if you can't ensure the short run player is going to cooperate, then you can't ensure any more than your min-max payoff, which is what you get if the short run player defects. So if you apply payoff bounds in the literature, they're going to say nothing in this game. They're just going to say the long run player gets at least her min-max payoff. And the problem is exactly that the long run player would like to teach the short run player that she is playing her deterring Stackelberg strategy, but if all she can teach her is that she fights a certain share of the time, that's not going to convince the short run player that she's playing the correct strategy, and it's not going to deter the short run player. Okay, so here's what our results imply in this setting. So I just remind you here of the payoff matrix, and let's let U1 lower bar of delta and U1 upper bar of delta be the infant soup of the long run player's payoff over all Nash equilibrium at the discount factor delta. So then we have the following result, and the result is whether the long run player can successfully build a reputation here is going to depend on some parameters of this game. And so what are the parameters? So the result is that if x plus y is less than 1, where, so here, look at the long run player payoff matrix. So her payoff from fighting against, when she gets the bad signal is 0, accommodating with the good signal is 1, and these sort of off-diagonal payoffs, if you fight after the good signal or accommodate after the bad signal, those are x and y. So if the sum of x and y is less than 1, then the long run player successfully builds a reputation. For any positive prior probability that she's the Stackelberg type, as she gets patient, her payoff is going to be at least her Stackelberg payoff of P. On the other hand, if x plus y is greater than 1, then the min-max payoff bound is actually tight. So for any discount factor less than 1, when the prior probability that she's committed is small, the long run player's payoff in any Nash equilibrium is going to converge to her min-max payoff. So of course, if she's thought to be the Stackelberg type with very high prior probability, she could do much better than this, because then the short run players are going to be deterred just by the prospect of the long run player truly being the commitment type. But this says that in the realistic case where the long run player is thought to be rational with high probability, she'll get her min-max payoff in every Nash equilibrium. So why does this sum of these payoff parameters x and y matter? It's because it determines whether the long run player's payoffs are supermodular or submodular, with the order that action A is higher than action F and signal C is higher than signal D. So what this says, if the long run's payoffs are strictly supermodular in her own action and signal, then she secures her Stackelberg payoff, and these payoff bounds in the literature are far too loose. And on the other hand, if x plus y is greater than 1, the long run player's payoffs are strictly submodular with respect to this order, then the long run player gets her min-max payoff in every equilibrium, and actually these existing payoff bounds are tight. So why is this? So let's first think about the supermodular case. And let's consider the deviation where the long run player always plays her Stackelberg strategy, the usual deviation where she hopes that by doing this, she'll convince the short run player to best respond. Is it going to work? Well, eventually, as we already discussed, the short run players are going to learn that the marginal distribution over the long run player's action is approximately the one generated by this Stackelberg strategy against whatever equilibrium strategy the short run players are playing. So like as we mentioned, in this case, the short run players, for example, if they're cooperating, are going to learn the long run player is fighting with probability 1 minus P, accommodating with probability P. But now, by strict supermodularity of her payoff in her signal and action, the unique optimal way for the long run player to hit this marginal distribution over her actions that's generated by her Stackelberg strategy is actually to play her Stackelberg strategy rather than some other strategy that might yield the same marginal. So in our language, that says that in the supermodular case, the Stackelberg strategy is confound defeating. It defeats, from the long run player's perspective, any possibly confounding strategy, such as that strategy of uniformly mixing between accommodate and fight in a way that gives the same distribution over her actions. Now, the short run players are going to realize this. And so they're going to realize then that whenever the marginal is the one generated with the Stackleberg strategy, the long run player, when rational, is actually going to be playing the Stackleberg strategy. And so that is going to eventually lead them to best respond to the Stackleberg strategy itself, not to a different strategy that happens to give the same margin. And that's going to give the long run player, allow the long run player to secure her Stackleberg pay.
Alex, I'm sorry, could you elaborate a bit on the third bullet point? I think the argument is very clear otherwise, but could you be a little bit more explicit on why the supermodularity defeats any possible confounding others?
Yes. So strict supermodularity here means that so for the long run player, remember, accommodate is always dominant. For any short run player, whatever signal I get, I'd rather accommodate than fight in the stage game. But strict supermodularity here, this case where x plus y is less than 1, means that accommodating for me is, so fighting is always costly for me. I'd always rather accommodate. But strict supermodularity is that fighting is less costly when I get the signal that you or me, when I get the defect signal. Right, so fighting is always costly, but it's less costly when I kind of get this signal that you fought. And so that implies that for a given marginal over my actions, for a given share of the time I fight, if I'm sort of constrained to fight that share of the time, I would rather fight when I get the signal that you defected. Oh, sorry, you're muted.
Sorry. I was saying, as opposed to just randomizing and doing it in a state-independent way. That's
exactly. We'll see actually in the next slide how things are different in the submodular case.
Yeah.
Okay. So actually, we can turn to that now. So what about the submodular case, where I'm saying that actually long run players can get her min-max payoff in every equilibrium? So in this case, this is exactly the opposite case. This is where, okay, again, fighting is only costly, but now fighting is more costly when I get the signal that you defected. So actually, if I'm going to fight a certain share of the time, I'd rather fight when I get the signal that you cooperated. So in that case, for any given marginal of my actions, I want to match the times that I fight to the times that I get the signal that you probably cooperated. And so that means that I'm always going to end up fighting weakly more when I get the C signal than the D signal. And now, of course, if you think that I'm actually the Stackleberg commitment type, then that may deter you, but that's not the case we're interested in. We're focusing on the case where the long run player is thought to be rational with high prior probability. And that implies that since your beliefs are a martingale, almost always you think that I'm going to be rational with high probability in equilibrium. And so since you're going to defect when you think I'm rational, this means that in equilibrium you're almost always defecting, and I'm going to be min-maxed.
So Alex?
Yes.
So can I, so of course this is, this is meant to be like suggestive of the mechanics and your general result, but as I understand it, even your general result is under, we're in a structured setting where we have, I'm seeing something about actions when the long run player was conditioning those actions on a private signal. But the mechanics of this seems to suggest just a more abstract, class of results about partially identified long run player behavior. And so we could say, given whatever, take whatever abstract version of Fudenberg and Levine 92 without the identification condition, and say, basically for any commitment type, there's the set of stage game strategies whose play is consistent with what you would observe if that commitment type were playing. And then, so do we have results that sort of say, if I'm, we could talk about being conditionally dominant or dominated relative to that set of beliefs about what I'm doing, where, I'm dominant relative to that set of beliefs if for any best response to any belief in that set, belief over that set. I want to play, I want to play a certain action. I'm dominated if for any such belief I don't want to. And so could we get like analogous results that are all just about this sort of abstract partial identification
so this is a perfect segue into our general model where we generalize this as far as we know how. And so so this is how far we know how to generalize it. And so if you see if anyone has any other ideas, we're very open to them. So exactly, this is exactly what we do. So how do we generalize beyond the example? So we're actually going to have a slightly curious general model with 3 players, a long-run player and 2 short-run players in each period, 1 each moving before the long-run player and after the long-run player. Why? Because we want to accommodate both games like the deterrence example, where the short-run player moves before the long-run player, and communication games where the short-run player moves after the long-run player. And we can have both at the same time, short-run player moving before, short-run player moving after. We have a general finite action, finite signal stage game. We have an arbitrary finite set of commitment types, so not just the stack over type, including types that mix, which we want to allow because sometimes, in general, the stack over strategy can be mixed. So even in our deterrence game, the long player actually could do better by committing to a strategy where, when they get the nice signal, they accommodate. With the mean signal, they mostly fight. Maybe sometimes they accommodate then too. That would give them a higher payoff while still deterring the short player. And well, of course, our focus is. The key for us is that even if the long-run player's action is observed, her strategy is not identified, we can also allow imperfect monitoring of the long-run player's action. So we'll allow that as well. Okay, so here's the model. So we've got 3 players in the stage. Game player 1 is our long-run player, and short-run player 0, who moves before the long-run player, short-run player 2, who moves after the long-run player. So in deterrence games, there's no player 2. There's just the short-run player who moves and then the long-run player. And in communication games, player 0 is nature. This is just a draw of the state. Then the long-run player is the sender, sees the state, sends a message, and player 2 is the receiver. Those are our leading applications. Players choose actions AI in some finite sets. Actions generate signals. So action AI is going to generate some signal YI according to some distribution rho I. These are all finite. We're going to assume that the signal of player 0's action has full support, and that the signal of the long-run player's action statistically identifies her action. So the long-run player's action may be observed imperfectly, but it's going to be statistically identified, whereas the long-run player's strategy, of course, is not identified. In general, is not identified. So the long-run player strategy is going to be a function from the signal of player 0's action to the long-run player's own action. And the timings as follows. First, player 0 moves and takes some possibly mixed action alpha naught. Then player 1 privately sees some signal of this action of player 0. It's going to take her own action alpha 1. And simultaneously with that, player 2 is going to take his action alpha 2. So we'll come back to this later, but to capture communication games where we really want to think about player 2 moving after player 1, we're thinking about an action of player 2 as being a mapping from player 1's action to player 2's action. We'll come to this.
Alex?
Yes?
So the class of settings I was asking about is less structured than this. So I guess I was asking, so let's say you have a short run, you have a short run player and a long run player, and you have a function of their action. The signaling structure is just a function of their action profile, stochastic map of their action profile, and we could still ask about.
That sounds more structured than this. That sounds like no player 0.
I mean, fine. So short run players, and it's and I'm thinking of the normal form of your stage game. So like, I guess I'm saying like the fact that what I'm choosing is is a function of something I've observed. Like that's a lot of structure on what my stage game strategy space looks like. And the logic that you gave seemed to be just about, I'm only partially identifying my the long run player stage game strategy, and I'm looking at, you know, dominance in the dominance relations between strategies within a given realized identified set. And it just so happens that because this thing, you know, has a flavor of my action is responding to like I'm choosing an action as a function of a signal, like fine, then the set of deviations that live within a given identified set looks like the set of deviations in Lin and Lu. But I feel like that specific structure doesn't seem crucial to the logic of these like conditionally dominated strategies or conditionally dominant strategies in the example.
So I think I'm missing some subtlety here. So let's talk about it later.
Sorry, I can, but yeah.
Sorry. Maybe just to add.
Yeah. Go ahead, Daniel.
Oh yeah, so I think Elliot, we have two equivalent definitions that we'll use for our kind of main result. One of them is going to use this kind of structure, the optimal transport definition. We'll have another definition that essentially just says among all of the partially identified strategies, you want to be the one that's uniquely optimal. And that definition should lift nicely, but we don't know of any kind of natural applications maybe where we use it. So, but the equivalence will rely on the structure, nothing else will. And the argument will go through with the more general definition for the setting that you care about, I think, if I understand.
Okay, thank you.
Okay. Okay, so payoffs, they depend on, so player zero's payoff depends on their action, player one's action, like the short player zero, who's like our short run player in a returns game. Player one's and two's payoffs depend on the signal of player zero's action. Like in a returns game, or like in a communication game, y0 would be the state, and they depend on both of their actions. Okay, so some notation, B of S1, this is a set of best responses to long-run player strategy S1 of the short-run players. So in particular, this is a best response of the short-run player to long-run player strategy, and then a best response from, the player two, the after-moving, the late-moving short-run player to the to alpha naught and S1. So then, given that notation for any strategy S1, we can define the corresponding commitment payoff for the long-run player to be the worst payoff she can get when she plays S1 and the short-run player is best respond. Okay, we'll need a little notation to state things formally. So this is notation for some distributions over things induced by the player's strategies. So first, can you guys see my cursor here if I move this around? It's potentially useful. So this phi of alpha naught S1, this is the distribution over the long-run player's action induced by player zero's action and the long-run player's strategy. Gamma of alpha naught S1 is the joint distribution over the signal observed by the long-run player and long-run player's action induced by alpha naught and S1. P is what's observed. So this is the distribution over public signals induced by alpha naught S1 and alpha 2. So these are the signals of the long-run player's action and then also the player 2's action. And finally, for any joint distribution pi, we'll note marginals by pi x. So in particular, the y naught marginal of gamma is the distribution over player zero's actions, and the A1 marginal of gamma is the distribution over the long-run player's action. Okay, so we're considering a repeated game. Long-run player has discount factor delta. A public history, so getting to Jeff's question, is the history of the signals of the long-run player's action in periods 2 and player 2's action. So we don't have signals here of the the short run players. So in particular, what's important here is that why not the signal observed by the long run player is not observed to future short run players. So as we discussed, and Daniel, I will think about this, I suspect that we could introduce some additional signals of player zero's action as long as they're symmetric between the symmetrically observed by the long run player and the future short run players. But we need to think about that. If the long run player's type is perfectly persistent, drawn from a finite set with prior mu naught, and as the standard reputation models, we've got our rational type who maximizes her expected discounted payoff, and a bunch of commitment types who always play the same stage game strategy. So for instance, the Stackover type we mentioned. And as before, U1 lower bar delta and U1 upper bar delta, those are the infant soup of the long run player's payoff in any Nash equilibrium of the repeated case. And we're interested in public strategy profiles where each player's stage game strategy depends on this history of public signals. And this is essentially without loss because the long run player is the only one with private signals, and there's no reason for it to condition on that, given that the short run players will not be doing so or don't observe this. Okay, so let's move towards stating our main result. And we first need this definition, which is exactly from Freudenberg-Levine. And this is what I mentioned earlier, an A-to-confirmed best response to a strategy with long-run players is a best response to some strategy that looks A-to-close to the long-run player strategy. That's what this is saying. So given some number eta and a long-run strategy S1, short-run player strategies are A-to-confirmed best response if there's some other long-run player strategy, S1 prime, that generates signals within public signals within eta of those generated by S1, to which the short-run player strategy is a legitimate best response. And B eta S1 is instead of eta confirmed responses to S1. Okay, now here is a transport problem that we're going to use to define this notion of confounded feedingness in our models. As Daniel mentioned, there's other ways you could define this, but this is going to be the easiest one to state and apply in the problems we're interested in. So this optimization problem, OT of rho phi alpha 2, what is this? This is the problem of choosing a joint distribution over the long-run player's signal and action with fixed marginals, rho and phi, so as to maximize the long-run player's payoff when the subsequent moving short-run player takes alpha 2. So a bit of a mouthful, but this is conceptually this is not rocket science at all. We're just choosing a joint. Basically, the long-run player is choosing how to correlate the signals she's observing, the action she's taking, given that the marginals over those things are fixed, to maximize her payoff when player 2 is taking alpha 2. And so, again, in our deterrence game, there is no player 2. So in our deterrence game, just drop this alpha 2 business. It's just how do I, for a given marginal over the signals I see and the actions I'm taking, how do I correlate those things to maximize my payoff? And here's our key definition. A strategy for the long-run player S1 star is confounded feeding if, against any zero confirmed best response, the induced joint distribution over the long-run player's signal and action is the unique solution to this optimal transport problem. Another way to put that is that this strategy kind of undetectably dominates any possible confound. So for any other strategy that gives the same marginal over long-run player action, so going back to our example, for example, the strategy just randomly fighting and accommodating, we want the Stackover strategy to give that same marginal so that the short-run players couldn't detect if the long-run player is playing one strategy or the other, but give the long-run player a higher payout.
Can I ask a very quick question? So existence of such a solution to OT is given to you by finiteness, I guess, and everything else. So here the whole thing is about uniqueness. Is that, am I understanding this correctly?
Yes, but we're describing here a condition of a particular strategy. So this OT problem has some solution. We say that a strategy S1 star is confident defeating if that strategy is the unique solution to this OT problem.
Right.
Exactly. And if there's in cases where this OT problem does not have a unique solution, no strategy will be confident defeated.
Exactly. But the existence is not a problem. There is always at least one OT because of the finiteness of a game, essentially. Yeah.
Correct.
Okay.
Yeah.
Thanks.
Yep. And in general, and this is this is easy to check in applications. In general, this is equivalent to some notion of strict cyclical monotonicity. If you know what this is, in monotone supermodular games, this is just monotonicity. Okay. Key implication of confident defeatingness is that at any history where the short-run players expect the signal of the long-run player's action to be close to those that are generated by the Stackelberg strategy. Okay, there's a detail that we need this both unconditional on the long-run player's type and conditional on the long-run player actually being rational. The short-run players have to expect the long-run player to actually be playing a strategy close to the Stackelberg strategy, not some very distant strategy that happens to give the same margin. This is what this says in math. I'm low on time. I'm not going to go through it. The logic is just that if this weren't true, then by confident defeatingness, there would be another strategy for the long-run player that would give her a higher payoff while generating the same margin. And so that would be a strictly profitable, undetectable deviation for the long-run player, so she would do that. So this is the key implication of confident defeatingness. Again, once the short-run players think the signal distribution is going to be close to what the Stackelberg strategy gives, they actually think the long-run players can be playing the Stackelberg strategy when it's confident defeating. Okay, one more definition before we state our theorem is the following. So confident defeatingness is our key notion. Essentially, this takes care of confounding by rational play. If the Stackelberg strategy is confident defeating, the short-run players are not going to think the long-run player is playing another strategy with the same margin. But what about the possibility of confounding by other commitment types? So in our deterrence game, what if the long-run player was possibly committed to this strategy of randomly fighting or accommodating with the same probabilities that the would be generated by the Stackelberg type? That could also be a problem for the long-run player, because now the short-run players could think not that the long-run player is rational but playing some other strategy, but the long-run player is committed and is a non-deterring commitment type that generates the same distribution of her actions. So we need to rule this out also. And so we say that a strategy is not behaviorally confounded if there's no other commitment strategy that induces the same distribution over signals against some zero confirmed best response. Now, this condition is generically satisfied when the distribution over the signal observed by the long-run player is exogenous, as in communication games where there's no endogenous action by a before moving player 0. This is much more restrictive and is not generic in games like the deterrence game where alpha node is endogenous. And so we actually want to ultimately relax this condition, and we're gonna, but I think I'm not going to get to that today. So in the paper, we have a more general version of our theorem that doesn't require behavioral confounding and instead gives a payoff bound for long-run player as a function of the prior probability on the desired commitment type relative to other possibly behavioral confounding commitment types. But here, we're just going to assume that there are no behaviorally confounding types. Okay, and to get to our theorem, let me first remind you of Fiedler-Levine's theorem, which is the following. It says that for any strategy S1 star to which the long-run player may be committed, that's what this omega is the set of possible commitment types. As the long-run player gets patient, she can secure at least the payoff she gets by committing herself to this strategy S1 star when the short-run players play their least favorable zero confirmed best response, not actual best response. That's what the 0 is. B0 S1 star, these are the 0 confirmed best responses to S1 star. Okay, our main result is that if in addition S1 star is confound defeating and not behaviorally confounded, we can get rid of that 0. The long-run player is going to get her actual Stackelberg payoff, the payoff she gets by committing herself to S1 star and inducing the the least favorable actual best response rather than 0 confirmed best response. And so if you look at it, you might say, oh, what's the big deal? We just got rid of this 0, hardly matters. But no, we've seen that this makes a big difference in many games. So for example, in a returns game, this is the difference between the long-run player being in charge just her min-max payoff and actually getting her stack reward. And in general, in our kind of game with long-run players, payout strategy is very much not identified. There can be a big gap between a V naught and a V. Okay, I have about 5 more minutes. Let me decide how I want to use this time. Essentially, the proof goes as follows. I'll take maybe 1 or 2 minutes to describe the logic of the proof. So first, if the long-run player plays a stack overwork strategy, the short-run player is going to learn the marginal over her actions, as in standard reputation results. So here's the lemma here is we take in a form due to Olivia Gosner's nice entropy-based argument. It also essentially goes back to Gutenberg-Levine in broad strokes. Then we say that because S1 star is not behaviorally confounded, eventually when the long-run player is following S1 star, the short-run players will come to believe the long-run player is either S1 star or is rational and is not some other problematic commitment. This is a learning argument. Then we say that, and moreover, since S1 star is confound defeating, once the long-run player knows, once the short-run players know the long-run player is either S1 star or rational and is generating signals close to S1 star, then they've got to be playing a strategy close to S1 star. And the short-run player is going to best respond to S1 star. This is where so this is confound defeating. This implies short-run players are going to best respond once they know the marginal and they know the long-run player is either rational or S1 star. And then we put everything together and say, okay, so if the long-run player always plays S1 star, short-run player is going to start best responding before too long, and long-run player will get her stack reward. We can also drop this not behaviorally confounded business at the cost of semantic complexity. Okay. In one-dimensional supermodular games, when is a strategy confound defeating? In other words, when is it the unique solution to this OT problem? It's exactly when it's monotone. And so this is related to the fact that in one-dimensional optimal transport with a strictly supermodular payoff function, the unique solution to this transport problem is the comonotone transport plan or a comonotone coupling between these two variables. And we also have a corresponding upper bound on payoffs, which is that, as we saw in the deterrence game, if long-run player is thought to be rational with high prior probability, she can't get a better payoff than she could by committing herself to any monotone strategy. And so we have not just this lower bound, but a fairly tight characterization of the patient long-run player's payoff in these monotone supermodular games. Okay, finally, how about communication games? So our results have stark implications for repeated signaling games where the sender's preferences over the receiver's actions are independent of the state. So in particular, if we take a signaling game where the long-run player's signaling cost is strictly submodular, so her signaling cost is strictly submodular in the state and action, so her payoff is strictly supermodular in state and action, like in the spent signaling game where my cost of sending signal A, if I have ability theta, is A over theta, then the long-run player can secure her payoff from committing to any monotone signaling strategy. And this follows from our general result by viewing your player 0 as nature and viewing player 2's action as a mapping from the signal sent by the sender to some response. And our general results from the one-dimensional supermodular case apply here if the long-run player's payoff is strictly supermodular in her action and her state for any strategy of the receiver. In other words, for any mapping that the receiver is using from the signal sent by the sender to the receiver's action, And that's going to hold when the sender has a submodular signaling cost and her preferences are separable in the state and the receiver's action. So that's why, right, the reason we need the state-independent sender preferences is that we need this submodularity for any function from A1 to the receiver's action. And so that needs this kind of additive separability. It's not a modular for any fixed receiver response, because in our model, the receiver is moving simultaneously with the senders. For strategies, this mapping from the sender signal to the receiver's action. Okay, and then finally, what about cheap talk or Bayesian persuasion games? Well, so we literally look at a cheap talk game, then it's, as Francesco said, this is a game where the long-run player just doesn't directly care about the correlation between the messages he sends and the state, because her message is cheap talk. So no strategy is confound defeating. So if you just apply our results literally to some repeated cheap talk game, they don't tell you anything. But we ask, when can you perturb the sender's payouts in these games with the introduction of some small signaling cost, so that this payout function could be strictly supermodular, and then when do we get some selection then? And so we can ask the question of what persuasion mechanisms can we provide a reputation foundation for by augmenting the sender's payoff with some small lying or deception cost? And the answer is that it's ones that are monotone with respect to some order on states in the receiver's action. And we talk about what persuasion mechanisms that is. So for example, that's any deterministic persuasion rule, so any partition of the state. It's also any linear partition with randomization at the endpoints, but it's not any possible persuasion mechanism. So long story short, there's a foundation for persuasion mechanisms with state-independent sender payoffs that we get by perturbing the sender's preferences over the messages she sends to have some small lying or deception cost, and this provides a foundation for a large class of persuasion mechanisms. Happy to chat more offline, but I'm already a couple minutes over, so let me just summarize and conclude. So what we do in this paper is we introduce a model where players develop a reputation for actions that they're going to play, but not necessarily conditional actions, functions from some signal that they observe to what they play. And we show this has applications, particularly to deterrence and communication games. Our main results identify conditions, namely confound defeatingness and not being behaviorally confounded, that ensure the long-run player can secure her stack overage payout. We show that in one-dimensional supermodular games, the long-run player secures her stack overage payoff if and only if the stack overage strategy is monotone. In general, this is its stack overage payoff is strictly U1 cyclically monotone. We talked about implications for deterrence in communication games and a foundation for the commitment solution in repeated signaling and perturbed cheap talk games with state-independent sender preferences. There's also some extensions, but let me not discuss those in the interest of time and instead respond to any questions someone has. If you could talk about some possible extensions and discussions. Okay, thanks.
Great, thank you very much. So yeah, now there's time for questions. So first, Elliot had to rush off, but yeah, Jeff, if you have any last questions or comments.
I don't have a question. It was a very nice talk. I'll just make a quick observation that was just kind of useful for me to condense some of the intuition to a simple example. Suppose we have a cheap talk game with common interests where the sender sees the state of the world. The sender and the receiver both want the receiver to take an action that matches the state of the world. And the sender has to communicate what state of the world she's seen. And of course, the efficient, kind of the obvious equilibrium is that the sender tells the truth. But of course, there's an equilibrium where he's thought to just randomize, and so it has no content. And so you want to say why would we expect that the receiver should believe that the sender is telling the truth? Well, if we add a little lying cost, then the best way to match the marginal distribution that comes from telling the truth is to actually tell the truth. And so kind of the obvious equilibrium is selected by kind of a very straightforward application of this idea.
That's a good example. Thanks.
One thing, there are a few subtleties there though, because in the common interest game, the sender's preferences will also be state dependent. And so kind of that's the intuition, but our results actually can't apply to that setting. And it's a little bit tricky to kind of work through which strategies survive or not.
Can I actually wanted to ask exactly about this, the preferences of a sender being type independent. I mean, I find it hard to believe that you can't, generalize this a little bit, assuming some sorts of type independence. I mean, so I understand that in your model, the states are entirely just nobody cares about the states themselves. You just use them to figure out what actions or strategies you want to take. But it could be that some sort of monotonicity, for example, should. I mean, have you guys thought about this, or am I missing something very fundamental that makes it unbelievably hard to do? I don't know.
Well, so in general, the key is this: we need the sender's preferences over the state and the message she sends to be strictly supermodular for any strategy of the receiver. And if there's not additive separability between the state and the receiver's action, that is generally not going to be the case.
So, but I mean, I'm sorry, I'm not too familiar with supermodularity and all that. But for example, in the example that Jeff was making of common interest, so there's a natural, say, a monotonicity on the type space. It goes from 0 to 1. The optimal action for any theta is I suppose you could have, I don't know, you have finite things, but you could have that you get 1 if you match the state with the action, you get 0 otherwise, and things. Would that not have? So I'm just asking whether I suppose it feels like you've done in Italy. We have this expression: you've done 30, might as well do 31. It seems like you could. It wouldn't be that much to get to that, because it is true that there might be some interesting classes of games for which the type action relationship is particularly. I mean, it's kind of disappointing if you can't really explain the common interest game, right? In a way, that's what I'm trying to say, I suppose.
Yeah, we should think about it.
I was thinking that this very special common interest cheap talk game, while it may not fit I mean, you don't necessarily have an ordering of the types and actions, so you can't necessarily fit it into that structure, but it seems like a direct application of just the general result. I'm going to mimic the commitment type, which is telling the truth. And I'm going to generate this distribution, which is the marginal distribution from telling the truth. The receiver is going to eventually believe that that's what I'm doing. And then he's going to believe that, in fact, the way I'm doing it is by telling the truth, because I have a cost of lying. And the best way for me to generate that distribution, just in terms of my own preferences, is to tell the truth. Maybe there's some issues with behavioral confounding, because I haven't really thought about that part of the problem. But like if the only commitment type was the truthful type, and it seems like, before you get to the structure that you use for your sender receiver games, if you just use the basic result, it seems like it should apply.
So
go ahead, Daniel.
sorry, I think in the common interest game, it's possible that it applies. So we need this strict supermodularity for any.
Yeah, this common interest game is a very special game. I brought it up simply because it just seems like a very direct way to point out what's happening.
I need to think about it, but I'm not 100% sure, because, for example, suppose that the receiver, for some reason, thinks that the sender is lying. Okay, so when the sender says 1, the receiver is inclined to take 0 and the opposite. But maybe, you know, the receiver thinks the sender is doing that, the rational sender is doing that just enough. The receiver ends up indifferent when there's also a chance the sender's committed to actually telling the truth. And then the sender ends up indifferent, or, you know, even with the small lying cost, maybe the receiver tends to disobey the sender a little more than average, and actually maybe you could cook up a bad equilibrium there. I'm not 100% sure.
So it would be useful if so, because like, you know, without following all the details, I'm just trying to see. I'm trying to rescue the Fudenberg-Levine argument using the confound defeating property. So, you know, the way I would rescue it is I say, well, we have some equilibrium. The long run player's payoff can't be smaller than what he would get if he mimicked the commitment type. What would he get if he mimics the commitment type? Well, after some finite history, he would convince that the short run players that his marginal distribution of actions was the same as the one that came from truth telling. And if the short run players believed that, and they also thought that he had a small lying cost, then they would think the way he's actually doing this is by telling the truth.
Right, but I don't. But the issue is that you know, what you need, again, what we need is that the long run player's payoff is supermodular in the state and her action for any short run player strategy, or any short run player strategy that's a zero confirmed best response. And so if it's a best response, so if it's a zero confirmed best response to the short run player to think the long run player is lying, the long run player strategy might not be supermodular in that way, even with a small lying cost. So I need to think more about it.
I see.
I suspect actually that you can probably cook up a bad equilibrium.
I see. Well, okay, so that would be pretty instructive then.
Thanks. Yeah, we should think about it. Yeah, right. So so again, all our leading examples here are these you know, deterrence games. The short player moves first, or then these communication games. But there are results have bite for this, you know, state independent preferences case, exactly so that we can, you know, like what's in the slide now, we can, you know, the relationship between A1 and theta, which would matter for supermodularity, that's independent of the short players of player 2's strategy. Otherwise, it may be hard.
Okay, I see the point now.
All right. Do we have any last question? Otherwise, I guess it's a good point to close the official seminar. Let me just announce that next week we have Arina Nikandrova, who's going to present data linkage between markets, hidden dangers, and unexpected benefits. Yeah, I hope you come back for that. And then all that remains is to thank our speaker Alex and our and Daniel, of course, for looking at the chat and contributing to the discussion, and yeah, Jeff and Elliot, who had to leave, our panelists. Thank you very much.
Thank you.
Recording stopped.
Yeah, actually,